Imagine a world where machines don't just recognize faces, but understand the subtle flicker of a gaze, the micro-expression of emotion, or the unspoken tension in a pause. That's not science fiction. It's the frontier of multimodal AI, and it's evolving faster than ever. Today, we're diving deep into a breakthrough that's redefining how AI sees, hears, and understands the world. The rise of vision language models that go beyond image captioning to interpret the full context of human experience. Let's start with the basics. For years, AI models were trained on isolated data, images alone, text alone, audio alone. But real human intelligence is multimodal by nature. We don't just see a dog, we hear its bark, feel its fur, understand the emotion behind its wagging tail. To mimic that, researchers began building models that could process multiple streams of information at once. Enter vision language models, neural networks trained on massive datasets pairing images with text. Early versions like CLIP, contrastive language image pre-training, learn to associate images with their descriptions by aligning visual and linguistic representations in a shared embedding space. But here's the key. They didn't just learn what something was, they learned how it was described, why it mattered in context. Now take that a step further. What if we could teach AI to understand not just images and text, but also the temporal dynamics of human behavior, the sequence of actions, the rhythm of speech, the evolution of emotion across time? That's where video understanding comes in. Recent models like Video-LLaMA, Flamingo, and CogVLM are pushing the envelope. They don't just analyze single frames, they process entire video sequences, tracking motion, timing, and causality. For example, a model can now watch a video of someone reaching for a cup, spilling it, and then wiping the table, and infer not just what happened, but why. The person was clumsy, or perhaps distracted, or maybe even injured. But here's where it gets really interesting, and technically profound. These models aren't just concatenating features from different modalities. They use cross-attention mechanisms that allow the model to dynamically focus on relevant parts of an image or audio stream when processing a given word or phrase. Imagine you're asking, what emotion is the speaker showing in the third second of the video? The model doesn't scan the whole video blindly. Instead, it uses attention to zero in on facial micro-movements, vocal pitch shifts, and body posture, then correlates them in real time. And it's not just about identifying emotions. Modern models can now reason about causality. They can answer questions like, why did the camera shake? And infer it was because the person dropped the phone, not just from the visual, but from the audio cue of a sudden thud and the speaker's gasp. That's multimodal reasoning, and it's built on architectural innovations like modality-specific encoders and shared transformer layers. Let's talk about how this works under the hood. Each modality, image, audio, text, gets processed by a specialized encoder. Images go through a vision transformer, ViT, audio through a time domain or spectrogram-based encoder, and text through a standard language model backbone. These encoders extract high-dimensional features, but the magic happens when these features are fused. The fusion isn't simple. It's not just adding vectors together. Instead, models use late fusion, early fusion, or interleaved fusion, depending on the task. In late fusion, each modality is processed independently, and their outputs are combined at the final layer. Early fusion combines raw inputs before any processing, but that's risky, because modalities have different scales and structures. The sweet spot? Interleaved fusion, where the model alternates between processing modalities at different layers, allowing for dynamic interaction and cross-modality alignment. This is where contrastive learning and self-supervised pre-training come into play. Models are trained on billions of image, text, video, text pairs, often scraped from the web. But instead of just memorizing associations, they learn to predict missing parts, like filling in a blank caption for a video, or reconstructing a missing audio segment. This forces the model to build a deep, coherent understanding of how different modalities relate. And now here's the most exciting leap. Generative multimodal models that don't just answer questions, they create new content. Imagine a model that can watch a short clip of a person struggling with a zipper, then generate a detailed, step-by-step tutorial video with voiceover, text annotations, and even animated overlays. That's not just prediction, it's multimodal generative reasoning. This is where models like PixArt, Sora, and Emu are leading the charge. They use diffusion models combined with transformer architectures to generate coherent, temporally consistent video from text or image prompts. But the real innovation? They can condition on multiple modalities simultaneously. For example, generating a video based on a script, a reference image, and even a voice recording. This isn't just about better AI assistance. It's about embodied intelligence, systems that can perceive, reason, and act in complex environments. Think autonomous robots that understand human gestures, or healthcare AI that monitors patient behavior through video and audio to detect early signs of dementia or depression. But there's a catch, and it's a big one. Despite their power, these models still struggle with common sense reasoning, long-term memory, and causal consistency. A model might describe a scene accurately, but fail to understand that spilling milk on a floor leads to a slippery surface, a basic physical intuition humans take for granted. That's why researchers are now exploring neural-symbolic integration, combining deep learning with rule-based logic systems. Imagine a model that doesn't just recognize a fire alarm but reasons. If the alarm is blaring and the smoke detector is active and the door is locked, then evacuation is necessary. That's the next frontier, hybrid architectures that blend statistical learning with symbolic inference. And finally, let's talk about the future, not just in research, but in impact. We're entering an era where AI can understand not just what is happening, but why, how, and what comes next. This has profound implications, from personalized education tools that adapt to a student's tone and facial cues, to mental health apps that detect subtle signs of anxiety in speech and posture, to intelligent tutoring systems that learn from a student's body language during a math problem. But with great power comes great responsibility. These models are trained on vast datasets that often reflect societal biases, gender, race, cultural stereotypes. A model might associate certain emotions with specific demographics or misinterpret cultural gestures. So transparency, fairness, and robust evaluation frameworks are no longer optional, they're essential. So where do we go from here? The future of AI isn't about better image recognition or faster text generation. It's about deep multimodal understanding, systems that perceive the world as humans do, not just as data points. It's about models that can watch a child's first steps, hear their giggles, feel the parent's nervous excitement, and understand the moment not just as a sequence of pixels and sounds, but as a human experience.